Today we will be learning section 3.1, which is exponential functions and their graph. In this section, we will learn about exponential functions, graphs of exponential functions, the natural base e, and applications. And throughout this section, the basic principle that we will use is plugging in values. The definition of exponential functions is exponential function f with base a is denoted by f of x equals a to the x power, where a is greater than 0 and a cannot equal 1 and x is any real number. The natural exponential function is f of x equals e to the x power. E is approximately 2.718281828, etc. This is known as the natural base. The exponential rules are a to the x power times a to the y power equals a to the x plus y power. A to the x power over a to the y power equals a to the x minus y power. A to the negative x power equals 1 over a to the x power equals 1 over a to the x power. A to the 0 power equals 1. A times b to the x power equals a to the x power times b to the x power. A to the x power to the y power equals a to the x times y power. A over b to the x power equals a to the x power over b to the x power. The absolute value of a squared equals the absolute value of a squared equals a squared. For graphs of exponential functions, refer to section 1.4 for transformations of graphs. The parent functions of exponential functions are y equals a to the x power and y equals a to the negative x power, and the graphs of these functions are opposites of each other. The graph of y equals a to the x increases, and on the positive number side, it increases quickly. The graph for y equals a to the negative x power decreases, and on the negative number side, increases quickly. A thing to remember when graphing is that if a is greater than 0 but less than 1, it behaves like y equals a to the negative x. Because of our exponential rules, a negative exponent becomes a fraction. An example of this would be a equals 3/4. Horizontal asymptotes are always one above or below the y-intercept depending on the transformations. Our first example for exponential functions and their graphs is f of x equals 2 to the x power. And since our exponent is positive, we know that it's going to increase on the positive side, so we're going to want to use an extra positive number. The numbers I chose for x are -2, -1, 0, 1, 2, and 3. And after you get those x values, just plug them right back into the equation, and you should get, for -2, you should get 1/4. For -1, you should get 1/2. For 0, you should get 1. For 1, you should get 2. For 2, you should get 4. And for 3, you should get 8. And our horizontal asymptote is 0. And now you just graph the equation.
If you ever find yourself stuck in the middle of the sea, I'll sail the world to find you.
Our second example for exponential functions and their graphs is f of x equals 1/2 times e to the negative 0.58 times x power. And since our exponent is negative, we know that it's going to increase on the negative number side, so we're going to want to use an extra negative number for our x values. The x values I chose are -3, -2, -1, 0, 1, and 2. And you just plug those right back into the equation, and for -3, you should get 2.85. For -2, you should get 1.60. For -1, you should get 0.90. For 0, you should get 0.5. For 1, you should get 0.28. And for 2, you should get 0.16. And our horizontal asymptote is 0. And now you just graph the equation.
I threw a wish in the well. Don't ask me, I'll never tell. I looked at you as it fell, and now you're in my way. I trade my soul for a wish, pennies and dimes for a kiss. I wasn't looking for this, but now you're in my way. Your stare
Compound interest is stated by after T years, the balance A in an account with principal P and annual interest rate R in decimal form is given by the following formulas. For n compounds per year, you use the formula A equals P parenthesis 1 plus R over M parenthesis to the n times T power. The different values of n are quarterly, n equals 4, monthly, n equals 12, annually, also known as yearly, it's n equals 1, semi-annually, n equals 2, weekly, n equals 52, and daily, n equals 365. For continuous compounding, you use the formula A equals P times E to the R times T power. Our compound interest example is a total of $12,000 is invested at an annual interest rate of 3%. Find the balance after 4 years if the interest is compounded A quarterly and B continuously. For this example, first we're going to do quarterly, and we use the equation A equals P parenthesis 1 plus R over M parenthesis to the NT power. And we're looking for our amount after 4 years, so we're looking for A. Our investment is $12,000, which is P. Our interest rate is 3%, so to get that as a decimal, you divide it by 100, which gives us 0.03. N is our quarterly number, which is 4, and T is the amount of years, which is also 4. Now you just plug all those back into the equation and you get your solution of $1,356.
It's a beautiful night. We're looking for something dumb to do. Hey baby, I think I wanna marry you. Is it the look in your eyes, or is it this dancing juice? Who cares, baby? I think I wanna marry you. Well, I know this little chapel on the boulevard we can go. No one will know.
Now we're going to solve for B continuously, and we do that by using the formula A equals P times E to the R times T power. And we're looking for our balance, which is A. We know P, our initial investment, is $12,000. E is our natural base. Our interest rate, which is R, is 0.03, and our time in years is 4. And you plug all that back into your equation and you get $1,356.
Do you ever feel like a plastic bag drifting through the wind, wanting to start again? Do you ever feel so paper thin, like a house of cards, one blow from caving in? Do you ever feel already buried deep, 6 feet under screens, but no one seems to hear a thing?
The radioactive decay formula is Y equals A parenthesis 1/2 parenthesis to the X power, where X equals time over half-life, Y equals amount remaining, and A equals initial amount. Our radioactive decay example is 210 years ago, there were 132,000 grams of cesium-137. If the half-life of cesium is 30 years, how much is there today? For this problem, we use our radioactive decay formula, which is Y equals A times 1/2 to the X power. We know we're looking for Y, which is our total amount. we know our initial amount is A, which is 132,000, and our X value is the time it from point A to point B, which is 210, over our half-life, which is 30 years. And when you divide that, you end up getting 7. So you plug all that back into your equation, and you get 1,029.6 grams of cesium-137 today.
Said all I want from you is to see you tomorrow. And every tomorrow, maybe you let me borrow your heart. And is it too much to ask for every Sunday?